mushroom cloud snakes skyward, hurling the atom's deadly radiation high into the heavens.
So let's be a little quantitative here. Suppose we take a sample of gas at 1 atmosphere pressure and 25 degrees C, and it's got a volume of about 1 liter. So I brought something here we can do this with. Your average latex glove. Hopefully it doesn't have any powder on it. I hate powdered gloves. So we'll use this as that's about 1 liter, I guess. And the gas in here is, so much for that. Sharp nails, I guess. The gas in here is just air. Note that it doesn't make any difference what the gas is because Charles' law applies equally to all gases. This better work because I only brought 2. Oh, if you think tying balloons is hard, you should try one of these suckers. Oh man, I won't be able to do this. So I'll talk while I do this. So what I'm going to do is trap some gas in this balloon. It looks like about 1 liter that I have in here. And I'm going to change the temperature, and we're going to observe a change in volume, hopefully, which will coincide with what Charles tells us here. You know, when you get your little finger stuck in the hole there, there we go. There we go. This thing is really tough. Okay, so that's about 1 liter of air stuck in this balloon. Now, suppose you did the following experiment. Suppose you were to cool it to minus 196 degrees C. How are you going to do that? Well, minus 196 degrees C just happens to be the boiling point of nitrogen, so you could do this by pouring liquid nitrogen on it. So put this under the camera here. There we go. So I've got it sitting in another Dewar flask, so I can pour the liquid nitrogen over this, and some of it will fall inside, and we'll see what happens to the volume of this thing. First of all, the rubber gets kind of brittle, so sometimes it goes bang. You can probably see better from where you're sitting that this is shrinking than from the camera angle. Okay, so I've cooled the gas that's in there to minus 196 degrees C, so according to Charles' law, it should shrink, and it did, of course. There's just as much air in there as there was before, but the volume has shrunk considerably. And if you look, I hope I can show this under the camera. If we look under the camera there, you might be able to see down here. I can see it quite clearly, but I don't think it'll show up on the camera, that we've actually managed to.
All right, Charles's law. Okay, Charles's law states that the volume of a given mass of a gas is directly proportional to its temperature at constant pressure. Okay, so Charles's law deals with volume and temperature only. Pressure is going to remain constant. Okay, they're directly proportional, meaning when one goes up, the other one goes up. Okay, we saw this in class, and you just saw it in the video. So when the temperature rises, the volume goes up. When the temperature goes down, the volume goes down. Let's say you left a basketball outside in the wintertime, or a soccer ball or something. Okay, so you had it inside, you left it outside in the wintertime. If you go outside, you'll see it's a little deflated. Why? Because the temperature went down outside, so the volume of your ball goes down. All right, with all that being said, a couple things. So here's your equation. V1T1 equals V2T2. Volume that you start with divided by the temperature you start with is equal to your new volume divided by your new temperature. Now there's a key here. You must have your volume here in Kelvin. The volume must be in Kelvin. So if you get something in degrees Celsius plus 273 is equal to Kelvin. Alright, so it must be in Kelvin, your temperature, every time. For all gas laws, you must have it in Kelvin. I'm stating that for a reason. It's big time. You got to make sure you do that. That being said, let's do a problem. All right, a gas sample of 40.0 degrees Celsius occupies a volume of 2.32 liters. If the temperature is raised to 75.0 degrees Celsius, what will the volume be, assuming pressure remains constant? Okay, if we go back up here, we need to remember our equation. It's right here. Let's write it down. So V1 over T1 equals V2 over T2. Let's apply. All right, first of all, 40 degrees Celsius. A sample of gas at 40 degrees Celsius. This is our starting temperature. But if you notice, it's in degrees Celsius. We don't like that. So 40.0 degrees Celsius plus 273. You can just consider that to be 273.000 if you'd like. Okay? Is going to get you 313 Kelvin. So there's our T1 here. So we know our starting temperature is 313 Kelvin. Scroll back up. All right, occupies a volume of 2.32 liters. There's our V1. Nothing to change there. So 2.32 liters. If the temperature is raised to 75 degrees Celsius. All right, here's our T2. However, it's in degrees Celsius. We don't like that. So let us convert to Kelvin. 75 plus 273. 348 Kelvin. So our new temperature here. All right, so for T2, it's 348 Kelvin. So we're heating it up. All right, on these problems, what you can do is, if you know the concept, and this one they're directly proportional and one goes up, the other one goes up, we're heating it up, so you should predict our volume to increase. So when you do this calculation, see if your volume increases. All right, we are trying to find V2. All right, with all that being said, I want to get V2 by itself. So I'm going to multiply times 348 Kelvin on both sides. Those will cancel out, leaving V2 by itself. So I'm going to multiply these from top to bottom. So 348 times 2.32 divided by 313. We got 3 sig figs here, so V2 is equal to 2.58. Kelvins cancel here, leaving me with liters. I said you can check to see if it makes sense. And so as we look at it, it was at 2.32 liters. It's now up to 2.58 liters. The temperature rose, so did the volume. It's a good way to check to see if you're on the right track. So there's our answer. And that's how you do Charles's law.